So I'm glad to introduce Professor Wang from Shandong University. So Professor Wang has long contacts with Russian mathematicians. He was one of participants of Russian Chinese seminars in China and in Russia. So, Professor Wang, please start.
First of all, I would like to take this opportunity to express my gratitude for the invitation from Moscow State University. I'm greatly honored to give a talk at the principal seminar of the Department of Probability Theory. I would like to express my gratitude to Professor Vladimir Voronov for organizing and arranging my invitation. I'm also thankful for the help he has provided me over the past decade. Without his assistance, I would not have been able to make the progress I have today. Additionally, I would like to thank Professor Jordan Stinov on this occasion. Thank you for his selfless help. I'm very happy to spend time with him. The title of my talk today is The Majorizing Measure Theorem for Log-concave-tailed Canonical Process. The talk is divided into three parts. The first part is the boundedness of Gaussian processes. I will first introduce the relevant result concerning Gaussian processes. The Abel Prize this year was awarded to the renowned French mathematician Michel Legrand. In fact, the result concerning Gaussian processes are related to the work for which he received the award. As stated in this, Legrand was awarded for 3 pieces of work: Settlement of stochastic process, concentration of measures, and spin analysis. Here is the main result of the Superman of Gaussian process, the Majorizing Measure Theorem. In fact, let's start by reviewing the simple case. For standard Gaussian random variable Kc and lambda, we have this the moment generation function. If Kc I are standard Gaussian variables, we can obtain this by trade-off approach. In fact, it is not difficult to obtain an upper bound for the mathematical expectation of the superman of a family of random processes. Obtaining a very tight lower bound is challenging. Legrand creatively invented the general training method for Gaussian processes, through which he derived the famous Majorizing Measure Theorem. Sorry. So if when Kci are independent standard Gaussian variables, if we want to get the lower bound, we need use these calculations by the Fubini theorem. We have this, and by the very simple inequalities, we have this estimate. Taking this delta is equal to square log n minus square log c. We have this. Then we have the lower bound is this, where c prime is a constant. When n have a lower bound, we have the lower bound of this is c times square log n. So in this classical case, when Ci are independent standard Gaussian variables, we have the very the tight lower bound. In fact, when Ci are standard Gaussian variables, and if we have such conditions, it means if in fact if under these conditions we also have such a lower bound where L is a constant. This A is in fact is the lower bound of the distance between two different Gaussian variables. This is the Sutakov moderation from Professor Voronov. I know Professor Sutakov is a Russian mathematician. So I learned a lot of from the Sutakov moderation. So when we just show like this, it is not difficult to up a lower tight lower bound for this simple case, but for a class of Gaussian process, Dagron introduced the basic notation of generic training method. Our work is to extend the generic training method to Log-concave-tailed process. When considering the boundedness problem of a family of stochastic process, it is often necessary for this family of random variables to have index t. At the same time, a distance measure need to be introduced. In this way, a generic functional analysis method can be employed to study such a method. So we for the Gaussian case, we introduce such a metric. Here, I will introduce the basic notation of generic training method. In fact, we need introduce the partition of T. This partition of T is called admissible. If the number of the set is the first set is 1, and the an the number an is lower than this for T belong to capital T, ANT denotes the unique element of AN which contains T. So Dagron introduced the training functional gamma 2 to replace Dudley bonds as the upper bound of Gaussian process. Here is the gamma 2. I call it Dagron functional, with the infinimer take over all admissible screens. Here, as always, this denotes the diameter of a set ANT. In fact, in the past century, many mathematics study such a problem. The most famous one is Dudley. Many current machine learning papers use Dudley bonds. However, Fernick proposed a conjecture that the upper and the lower bound should be the same order. So, in fact, Dagron solved this problem, obtained the Majorizing measure theorem. They have a lot of not so many form of this theorem, but in 2001, in this paper, he showed this very famous Majorizing measure theorem. In this talk, we make the convention that the constant L is not necessarily the same on even in the same equation. So let me review the main method of general training method to obtain the lower bound. in fact, to obtain the lower entire lower bound, we need to study the Sudakov minoration. Sudakov minoration for Gaussian process. For Gaussian process, the Sudakov minoration is this. Wang says this is a separated theorem. If 2 point of in the set is have a lower the distance of 2 point have a lower bound and have such a estimate. So Wang generic this Sudakov minoration to a very general condition. I mean the gross condition. So he found the Sutma of a process, the expectation of a Sutma of a process will follow the gross condition. What is the gross condition? So if a map F is a functional on a subset of T, if FH is greater than 0 for each subset H of T, and if H is a subset of H prime, FH prime is bigger than FH. So if the HL is divided by this ball is separated by this ball. This have a two parameter A and R, and satisfies this function F is called satisfies gross condition. So we can look at it. We said that the functional F satisfy the generalized gross condition with the parameter R is bigger than 8, and C star is bigger than 0 if for any integer n is bigger than 1 plus log 2 p, and for any a the following holds true, where m is this, and for each collection of subset h1 hm of t that are separated, we have such a gross condition. Even the gross condition is satisfied, how can find the lower bound of the expectation of Sutma of process? So Wang show under the partition scheme, if two functional satisfy the gross condition, this gross condition, so the lower bound of the functional satisfies gross condition should be the gamma 2 functional. So this gamma 2 functional is the lower bound of the functionals satisfy the gross condition. How to find this result? In fact, we need to construct a partition schemes. We should find people should find schemes of the partition of the T and find a partition to achieving the lower bound. So from the result of Sudakov minoration, how to find such a partition? So find such a partition schemes is very important for obtain the lower bound. So for Gaussian process, Wang found such partition schemes. So if B is belong to T, satisfies these conditions, and for any n is bigger than 0, set such a M, then there is the partition AK of B into set which have either of the following properties, the conditions 2 and condition 3. We will see the condition 2 means the diameter is the partition is smaller, and the condition 3 means if the parameter of the partition is not smaller, it should be satisfied the Groo's the Sudak So to prove the Majorizing measure theorem for Gaussian process, people need to obtain such a bond. For the lower bound, we see this 2 sub n and r sub minor j n is the lower bound. If the partition 2 partition satisfies 2, I mean if the t in a partition t belong to a set, and in a new partition t should belong to a subset of the former t, former A. So if the partition satisfies 2, so we set Jn plus 1 is equal to Jn plus 1, and if the partition satisfies 3, it should be said Jn plus 1 is equal to Jn. Constructing a geometric structure to obtain the Majorizing measure theorem is natural. So some people found we can use the tree constructor to obtain the Majorizing measure theorem. A kind of tree tau is our space T should with the following properties, given A and B in tau. If we satisfy this condition, then either A is subset of B or else B is subset of A, and tau has a largest element. If AB belong to tau and B is subset of A and B is not equal to A, we said B is a child of A. If C belong to tau, B is subset of C, and C is subset of A, implies C is equal to B or C is equal to A. So when denoted by CA, the set of children of A, thus we can define A is equal to PB if B belong to CA, and A is PA if A is the largest element of tree. It is convenient to introduce the set, such a set. So it is a supported set of this tree. Define the size of the trees, low tau. So low tau, we should such a functional. And if take the summa of all the tau, we can construct a so-called dual Majorizing measure theorem, and people can prove polynomial. I mean, one can compute a term in polynomial term for gamma 2. So Ding Jian and his co-authors in 2012 in Annals of Mathematics prove this theorem, the dual Majorizing measure theorem. And in this talk, my students and me obtained a geometric characterization for the Majorizing measure theorem for the log-concave-tailed canonical process. So let me give the definition of the log-concave-tailed canonical process. Consider an independent symmetric random variables yi. We defined the functional ui x. This is uix. The functional uix is convex for all I is bigger than 1. Assume this condition, and if xt is a supermer of ti times yi, x over t is called log-concave-tailed canonical process. Here, T is a subset of L2 space. We will introduce a new function, ui hat x. This function will be used to prove our result. So the most different the difference between log-concave-tailed canonical process and the Gaussian process is in the Gaussian process, the distance is that's a very classical distance, and the space is Hilbert space to obtain the lower bound of the expectation of supermer of process. So the growth condition, and Sudakov moderation, we will back to the growth condition. In this place, so the Sudakov moderation is a times square log m. This is because of the Gaussian process. So if we introduce this distance, we have such a form of the Sudakov moderation. However, if we consider log-concave-tailed case, this is quite different. So we need to introduce the new space and the new distance to obtain the Majorizing measure theorem. Latala introduce this, and he will introduce such a ball Bu. Bu is such a T. In fact, Bu standard new ball in this discussion. So when uix is xp for all x and I, BP is the unit ball in LP for P is smaller than P, and P smaller than infinite. When P is equal to 2, we have such estimator. So we can see NUT is upper bound by square U times T. T is Euclid norm, and is lower bound by square U over 2 times the Euclid norm of T. It should be rather to obtain that the UI hat x is such a bond, and it should be which implies this. So if P is equal to 2, NUT should be the Euclid norm in this case. But I should say even the P is equal to 2, this case is not the Gaussian case. It has such a little bit different. And if P is 1, in this case, we have this UI hat x has such a lower bound and has a upper bound for all the this. So we will have such a estimate, and we consequently we have NUT is bigger than square U times the Euclidean norm of OT, and also bigger than the U plus U times the infinite norm of T. So I will show if P is equal to 1, NUT is such a upper bound and such a lower bound. So for the ball, we have this estimate. So when P is equal to 1, in fact, this ball should be characterized by two distance. In fact, by two distance. So since UI is convex, so UX grows at least as fast as a linear function, and we will assume the following regular condition, which ensures UI doesn't grow too fast. For some constant C0, we have such a condition. This condition is often called the delta 2 condition. We will also assume that such a condition 5. So we introduce a function phi jst. Phi jst is a function, is an infinite of u, satisfies s minus t, belong to such a ball, and bjsr is such a t. We can say yjst is a family of distant, and bjsr is a family of ball. So we also introduce the admissible sequence of T, and this is the same to the Gaussian case. So Doug in his book, in 2014, he obtained the lower bound for the log-concave-tailed canonical process. So we can see in the last line of this is the lower bound of the superma of XT as the lower bound. So if xi is a Bernoulli, y is a Bernoulli sequence, so st is called a Bernoulli process. So Benders and Latala studied such expected superma of the Bernoulli process in the spirit of trying to review a long-standing conjecture of background called the Bernoulli conjecture. Benders and his co-authors obtained a full characterization of the expected superma of infinitely indivisible process, and settle postulate the conjecture proposed by Dagrand. Recently, Park and Pham obtained that the superma of generalized Bernoulli process is significantly larger than its expectation and can be covered by a set of half space in which the sum of measures is small. So the Bernoulli, where I introduced the Bernoulli process, the Bernoulli process is a very special case of the log-concave canonical process. In fact, if we recall the UIX, for this UIX is equal to XP. If P is infinite, is the Bernoulli process. However, the Bernoulli process don't satisfy the UI such a condition. So the proof of Bernoulli conjecture is very complex. Why is very complex? I will show in the Sudakov mandarin. This all the growth condition. This part is a times 2 sub 2 n over 2. So for the Bernoulli case, this is changed. And for the log-concave-tailed canonical process, this case is also changed. But we have the delta 2 condition. So we will construct a very not a very complex partition schemes to obtain this. But if the delta 2 condition is not satisfied, so the partition schemes can be not used. Latala and Benders they introduce a very complex partition schemes and based on so-called Latala principle to obtain the local the growth condition. So in my work, I obtained the dual Majorizing measure theorem for the log-concave-tailed canonical process. So I will introduce our result. So we define J0 bar is the largest number satisfies the condition. Given T belong to capital T and a probability measure mu on T, we define J0 bar T is equal to J0 T for any T belong to capital T. And for n is bigger than 1, we define JNT is equal to this. So here is a probability measure mu here. So why we called such a result Majorizing measure theorem, but we cannot say in the Majorizing measure theorem a measure in the theorem mu. In fact, the mu we can regard the mu is the another form of the partition schemes. So mu stands for the partition schemes, so that as the sequence increases and within that I mu t is this. So this is the functional we want to prove that. So we have such a theorem, and the conditions 4 and the condition 5 we have such a estimate. So in fact we have such a I mean the upper bound and the lower bound of the expectation of Superman of log-concave-tailed canonical processes. For this, we can get the dual Majorizing measure theorem. So, how to prove this theorem? We will introduce a parametricalized trace. In our trace, this is all the definition of the tree. So we also record such the notation of the trees, and we defined a new kind of tree, the parameterized separation trees to prove our main result. The parametered separation tree is denoted as this. So this sequence is a natural sequences, and NA and JN means functionals from tau to z. We will consider the number if n g appear without a set. So we how to prove this? We need to construct a tree. A tree. How to construct such tree? We use such a steps like a algorithm. Firstly, we select an arbitrary subset A of T as the initial set, and define JA is infinite, and AA is equal to -1, and this we construct A0. If this we set this and this, and otherwise we can choose arbitrary such a points, and such points we need such satisfy such conditions, and we set this JT, and define such a set. And step k plus 2 is a iteration. So we use the after the k plus 1 steps for the set is this. We also set this, and we choose such points, and taking this for find integral sequence, and construct the trees, and define the function nodes, and obtain the a k plus 1, and define a tree. The tree is in fact is a union of the partitions. So under the condition 4 and 5, we define the size of t. So size of t is a suitable of functional of parametric separation t, and we have the size of t is the lower bound and the upper bound of the suitable of the process. And in fact, we have to argue the following steps hold true. So the first one is the measure, the suitable of measure. In fact, is called the Fernic functional. Fernic functional is lower bound by the expectation of suitable of xt. So the step 1 is almost adequately to the proof of Wang's book, and step 2 and step 3 are the main contribution of our paper. Let's summarize each of them. In step 2, we define a probability measure mu associated each tree t tau, such that rho tau is lower than I mu t for such a t belong to such a trees. And in step 3, we will use the growth condition. We use growth condition. So the growth condition is quite different from the Gaussian case. Why? Because we introduce a family of distance. But for the former growth condition in Gaussian case, there's only one distant. So we will consider a family of maps, phi j bar, and with the following properties, and define the bjtz such balls. We can recall a set on such a t satisfies the growth condition. However, under this condition, we have such a growth condition, and I will say this condition is the delta 2 condition is very important for obtain the growth condition. In our proof of the growth condition, we use the method introduced by Professor Rama Van in Princeton University, and contraction principle. So if we follow the proof of Lagrange, we cannot obtain the growth condition for the log-concave-tailed canonical process. So if we witness the measures as an application or main result, we also obtain a Majorizing measure theorem on a finite t. In fact, in this case, we should assume a finite t. In fact, if t is not infinite, we cannot obtain the inequality in this 4. So under the delta 2 condition, we will have such a estimate. So in this, we will witness the measures mu. So it also can be regarded as a dual Majorizing measure theorem. So, our result can be regarded as an extension of bundles and his courses. So this is the reference of this paper, and thank you, спасибо.
Dear colleagues,
Елена Борисовна, пожалуйста.
excuse me, first of all, excuse me, please, I have some problems with the sound in my computer, and I would like to thank the professor for the excellent talk. Please, colleagues, your comments or questions, please.
Thank you.
I want to say the following. In case of the Brownian motion, everything will be much more simpler, okay?
Sorry?
Альберт Николаевич, немножко ближе.
Лена, подождите.
Проблема у вас со звуком, немножко поближе к компьютеру, и тогда вас будет слышно.
Носом в компьютер.
Отлично, сейчас хорошо.
Лена, помолчите. Suppose that your process X is the winner process. Then everything will be simpler, yes?
Yeah.
No, for example, interesting problem about supremo of the winner process when this process all times didn't reach the level minus A, for example.
Yeah.
Ульяна, может быть, поясните что-нибудь? Нет?
Yeah, Professor Shayev thinks if for the winner process, the Gaussian process case is still standard. But I think for the winner process, the set of T should be should have some conditions to this. In this case, the condition of T should have some conditions.
Yes,
So we
but
can see,
but if you consider winner process on random interval HT is random, then situation will be much more complicated even for winner process.
Oh, yes.
So in all your case, you consider interval T in some sense definitive, yes. But if interval T is random, then situation will be much more complicated, even for Brownian motion.
Yeah. It should be very complex. Yeah.
Ульянов, вы должны сказать. Альберт Николаевич, так Елена Борисовна у нас руководитель.
Maybe Vladimir Vasильевич, Professor Ульянов add some things or something else.
Yeah.
Not exactly, because it's not exactly my topic. So.
But if T is random, just say Professor Shayev say if T is random, I think this case is very complex. Yeah. Even W is a winner process.
Yes, it's true. It's true.
Maybe another questions or comments, please.
For Brownian case, there is our paper with Mark Yor, where we consider situation of interval T is random. Please read, by the way, this our paper. Yes.
Oh, thank you.
For winner process.
you see your paper with the Michael York.
Yes, yes.
Okay, thank you. I will study this. Thank you very much for your comments, sir.
And in fact, this topic is very interesting. If you have interest, we are ready to publish your paper in our journal Theory of Probability. Please send the corresponding paper.
Oh, thank you very much, sir. I will submit our result to your journal. Yeah, it's my honor.
Yes,
It's my great honor.
you have official invitation. You have official invitation to write. We are very interested. We know the paper of Sudakov, of course, but your new results will be interesting for everybody.
Thank you very much, sir. I'm very honored. Thank you, sir. Yeah.
Nikolai, one of his paper is already submitted to our journal.
Oh, thank you, Professor Wang.
Но не об этом.
Ну, не совсем об этом, да.
Да, не совсем об этом. Нет, сейчас много китайских ученых представляют статьи в журнале «Теории вероятностей». Много. Так что мы должны содействовать тому, чтобы они печатали у нас.
Maybe I translate for Professor Wang your words. Many known Chinese scientists now are presenting their papers to the Journal of Probability Theory.
Yeah.
So I translate the words of Professor Sharif.
Thank you, sir. Thank you. Yeah.
Maybe another comments, questions? If no, so I would like to speak about our next seminar. On our next seminar, it will be a talk of Yulia Makarova. She will present the materials of her PhD dissertation that was made on our department.
What is the title? What is the title?
The title of the talk, Branching Random Walks with a Few Types of Particle on Multidimensional Lattices. And the next seminar will be the last in this semester. And we will start on February as usually. So see you next Wednesday.
Ульянов, если вы хотите что-то сказать гостю, то скажите, потому что я не знаю его лично, а вы знаете же.
Владимир Васильевич, you have, please.
Не надо, Елена, не переводите это, он же, я специально
Нет,
говорю
у него звук выключен.
Володя
Владимир Васильевич, we cannot hear you. Vladimir Vasilyevich, we cannot.
Sorry. Yes. So we contact with Professor Wang quite often by WeChat, so it's not necessary to say something additionally to him now.
Yeah, thank you, sir. Thank you.
Thank you, Professor Wang, for interesting and deep talk. Thank you.
Yes, thank you, Professor Sharif. Thank you, Professor thank Professor Leonov for this very wonderful afternoon. Yeah.
So, bye.
Bye.
Now we finish our seminar. Professor Wang, thank you once more. Yeah. We will be very glad to see you maybe on another, maybe next year, maybe on spring semester. Thank you very much.
Thank you very much.
Okay, thank you, Hanchao, and hello to all Shandong.
Thank you, sir. Yeah,
Long friends.
yeah. Thank you, Professor Daniel. Yeah. Bye bye.
Okay.